We'll take a look at this triple integral. Find the volume under z equal x squared plus y squared and above the region in xy plane bounded by y equal x squared and y equal 1 and x equals 0. So we want the volume under this paraboloid, but above these equations in the xy plane. Now, it's kind of hard to draw this parabola down here in this line in the xy plane in 3 dimensions. So I'm going to make a separate graph for those. So the region down here in the xy plane that we're interested in is going to be represented by this. Like I said, I'm not going to make a mess and try to draw that here. So when we do triple integrals, let's say in this case here, this is opening along the z-axis. So the most natural thing to do would be to do z first, and then y, and then x. Now you could possibly do x and y, but definitely want to do z first. And another thing to remember, if we want the volume, our integrand is just going to be 1. So we're just going to be like a 1 here. And you don't even have to put in, since a 1 times anything is just anything. So I'm going to just leave it off. And so we're going to do dz, dy, dx. Now, in this case here, if we do z first, the best way to handle this is to imagine yourself standing in the region that you're finding the volume for. So you want the volume under this surface and above this. So just imagine standing down here like this. And again, we want above the XY plane, above the region XY plane. So our first integral will be in terms of z. So we're going to have a z equals something here and a z equals something here. And the lower bound is going to be wherever our feet are touching. So we're standing in the XY plane. And what is z when we're in the XY plane? It's just z is just 0. And again, always imagine standing with your head pointed like in the positive direction. So if we're doing z first, again, you're standing in the XY plane pointed in the positive z direction. And think of, where is your head pointing? Your head is pointing up towards this surface here. So your upper bound is going to be x squared plus y squared, like this. And now once you have done z, then you focus on what the projection is into the xy plane, because we're done with z. So now it's down to these two integrals. And again, usually when we get down to a double integral, let's say we want to do y first, we'll put arrows in the positive y direction. And remember, wherever the arrows start, they start down here on this equation, y equal x squared. And they end on this equation, y equal 1. And then the final thing you have to do is to say, okay, we're done with z, we're done with y, so we're just down to 1 dimension here. We just say to ourselves, how is this region projected on the x-axis? And actually, if you put y equal 1 here, you can see that x is going to be equal to 1 from this equation. So the values for x are going to go from 0 to 1. Mainly, you're just looking, okay, just focusing just on what values of x are covered by this region, it's x equals 0 to x equal 1. Now I won't go through the mechanics of integrating this, but it's just like a double integral. You're gonna except you do z first, substitute, then do y, and then do x. But again, let's think of how we set up the integral. Again, if you want to do z first, imagine standing with your head pointed in the positive z direction. The lower bound is going to be where your feet are. Upper bound where your head is pointed. That's its surface here. Then we've done with z, focus on the xy plane. Here again, let's say we did y first. Put arrows in your region in the positive y direction. Where the arrows start is y equal x squared. Where they end is y equal 1. And then finally, your last bound will always just have numbers because all you're interested in is what is projected onto your last interval, like on your last coordinate. So the projection onto your last coordinate, the values covered are x equals 0 to x equal 1. Sometimes when we do the last two integrals of a triple integral, we will find that converting to polar coordinates will make things much easier. We'll see that in the next example. And in this case, we want to find the volume under the surface z equals 16 minus x squared minus y squared and above the xy plane. So we want to find the volume in here. And what we're going to do is first integrate with respect to z and then x and y. So we're going to need to find out what the domain is in x and y. And when we see our surface here, to find domain x and y, we're going to have to find out where this surface intersects the xy plane. And we can find that by setting z equal to 0, because when z is 0, our surface is in xy plane. So let's do that. So z equals 0, 16 minus x squared plus y squared. And if we rearrange this, and we can write 16, of course, is 4 squared, and that looks like a circle. So we're going to have a circle in the xy plane, which is going to be where our surface intersects the xy plane. So it's good to draw what we have in the xy plane. So we'll have this circle down here. Again, that's this circle right here in the xy plane. And now, when we set up the triple integral, since we're just looking for volume, our integrand is just going to be 1. So like right here, we're just going to have a 1, or you can just, leave it blank because that implies 1. And then we're going to do dz dy dx like this. And so when we do triple integrals, the idea is this. Whatever our first integral is, like in this case, it's with respect to z, imagine yourself standing in your object with your head pointed in the positive z direction. So let's say you're standing in here and you're, with your feet on your lower bound, which is the xy plane, and your head is pointing up towards the surface. And then wherever your feet are touching, that's going to be your lower bound. Now, again, we want it, since z is first, we want it in terms of z. So we want to say z equals something here, z equals something here. So now, of course, down here, z is 0 on our lower bound because that's in the XY plane. And up here, your head is pointed towards the upper bound again. And what's the upper bound in terms of Z? That's going to be Z equals this. Z equals 16 minus X squared plus Y squared, like this. Now, the last two bounds, you go then into your 2D plane. So in other words, you're thinking, okay, how does my region project into the XY axis? And it projects into the XY axis on this circle. Now, in this case here, it's going to be easier to convert this to polar coordinates. Now, if you want to keep it in Cartesian coordinates, you could write this, the lower portion of the circle, as y equal negative the square root of 16 minus X squared. And then this is y equal the square root of 16 minus X squared. Now, this is the hard way to do it, but I'll show you the easy way in a second. So, again, all I did here was take the equation that we had of our circle, 4 squared or 16, and then solve for y. And take the square root. And then, of course, when you take the square root, you go to plus or minus. The minus is going to be the lower half of the circle, and the plus is going to be the upper half of the circle. So, again, I'm just going to write this temporarily. So, in this case, you would go from y equal negative square root of 16 minus x squared to y equal square root of 16 minus x squared. Remember, if we do y first, we're think of putting arrows in the positive y direction, and this is your lower bound and your upper bound. And then when you do x, it's just going to be from x equal minus 4 to x equal 4. Again, this is the hard way to do this problem. The easy way, when you get to this point here, is to convert the polar coordinates. And so what we'll do, remember in polar coordinates, a circle of radius 4 is just represented by r equals 4. And you remember your conversions for polar, x squared plus y squared is r squared. So we can simplify this whole integral by changing the polar. Now, in 3 dimensions, it's generally called cylindrical coordinates, where z is still z, but then you have r and theta. So you have dr d theta, like this. But when you convert to polar, you always have to include the Jacobian, which is r. So you always have to include this right here. So now let's convert everything. So we're still going to go from z equals 0 to our upper bound, which is this, but we're going to replace x squared plus y squared with r squared. Like this. And now, when we do our last two bounds, we're going to use r and theta. So if you want to do R first, put arrows in the positive R direction. Like this, where the arrows start, that's the lower bound because they're all starting at the origin. So there, R is of length 0, and they're ending on the equation R equals 4. And again, for our angle, we're starting at theta equals 0, goes all the way around to theta equals pi over 2. Excuse me, theta to 2 pi. The last one, 0 to 2 pi. So now we just have to evaluate the integral. Now it's just a matter of doing what we've done previously, except we have 3 integrals. So we're going to integrate with respect to z first. That's just going to give us z from z equals 0 to z minus r squared. So let me throw the r in here. dr e theta. This. And then substitute for z. Integrate again. And then this comes out to be 64. And you could actually even put that out front and integrate one more time. This is going to give us 64 times 2 pi, or what is that? 128 pi.